First off, thanks to the SPE section for inviting me to talk tonight. It's a pleasure to do so, and thanks to everyone who's given up some of their evening to listen today. So, as Nasir said there, I'm going to present some slides and some information on formation damage and laboratory evaluation. If you've got questions, use the Q&A box. I'll try and keep an eye on them during my talk, and if I don't get through all of them, we'll stop at the end and we'll talk about them as well. So I'll just turn off my camera so you've got some slides on it. Okay, so the subject tonight that we're going to talk about is improving drilling and completion decisions through laboratory simulations and visualizations. What we're really talking about here is the subject of formation damage. So what my aim tonight is a big subject to do. We've got drilling people in the room, completions people in the room. What I'd like to do is introduce formation damage and the study of it as more than just a concept that we all think about and try and avoid, and maybe think about how we can use it to make better decisions. If we can identify the potential for it to happen, if we can have good ways of identifying that, then we have a good chance of avoiding it or removing it later on. So what I'd like to do is maybe break it into 3 sections tonight. I'm sure we have a range of experience in the room, from people who know exactly what I'm talking about to people who have only heard of formation damage as a concept. So first off, I'd like to talk about what do we consider formation damage, and then think about during drilling and completion, what can cause it to happen and what that can look like inside the reservoir. Then we'll move on to thinking about how we can actually identify that. What do we mean by laboratory simulation, and what are the compromises that are taken with traditional techniques? Because this is a science that's been around for 30 odd years. There are compromises with traditional approaches, and that'll lead into the kind of the main aim of what we wanted to talk about tonight, which was how can we make improvements to studies in terms of the laboratory simulation side. I'll do a short section on that, and at the end, visualizations. This is a kind of exciting area in the industry, is how can we improve our understanding of simulation results by doing visualizations to get new insights and actually new metrics that will help us make decisions, select drilling fluids, select completion fluids, select ways of avoiding and removing their damage. So that's what I'd like to do tonight. And I'd like to show this slide first to sort of say, why should we all be talking about this? Now, this slide is actually, you can see at the bottom there, it's about hydraulic fracturing, but it's extremely relevant to anything in the reservoir, especially formation damage. And it's what were the most common reasons for jobs not meeting expectations. And you know, if there's drillers, completion guys on the call here, you'll be thinking, oh, well placement, design of the operations, the reservoir quality wasn't right. Yes, they're all important things, but dominant, over 50% of failures were due to not understanding the subsurface reservoir. And coming from a perspective of drilling completion, if what I'm going to show you now is what we do during drilling completion can affect the reservoir through compatibility issues, cleanup issues, then that's basically not understanding it properly, not planning properly how we drill, how we complete, not using full information is kind of setting us up for failure in this understanding of a reservoir. So with that in mind, what am I talking about in formation damage? And so, as I said, it's a phrase we've all heard. I just want to give it a really broad definition. It's anything that can have an unfavorable impact on production, injection, and it can be caused by anything in the life cycle of the well. So from that first second the drill bit enters the reservoir to the last drop of production or injection through completion, cleanup, workover, treatment, EOR, anything that we do in the reservoir, including production and injection themselves, can take the reservoir away from ideal behavior. Now we're going to focus in on drilling completion for the rest of the presentation. But I mean, these are the sort of things we talk about in information, and I'm sure lots of you have seen these before. Drilling mud. So when we're thinking about drilling, we have drilling mud. If the sizing is wrong, drilling mud can go into the formation, maybe deep into the formation. Fluid can be retained within the formation. Solids can go into the formation. Or when we try and produce, the mud cake isn't cleaned up properly. There's poor cleanup, and that blocks pores off at the wellbore and restricts production. Fluid retention is drilling our completion fluids going into the reservoir and then not being removed from the reservoir for chemical reasons, for compatibility reasons, for viscosity reasons, because we can't flow at a high enough rate or differential pressure through the near-wellbore. Fines. Now, in clastic reservoirs, everyone thinks of clay fines and they think it's a problem. We just chuck potassium chloride in and that'll stop clay. That's clay swelling that potassium chloride will help with. But what we see all the time in many reservoirs, if not all reservoirs, are some sort of clay fines which have potential to migrate within the pore network and then accumulate elsewhere in the pore network. So moving within a pore, moving between pores to block pore throats, to reduce the permeability and therefore the production or injection of a reservoir. Incompatibility, this is something again we see all the time. So scaling from injection water, for example, or scaling from production differential pressure, emulsions from completion drilling fluids interacting with reservoir fluids. This can be fluid or rock fluid. These are all sources of incompatibility. And then the last example, there's hundreds of damaging mechanisms, but another one that we see all the time, but not enough people think about, is bacterial, microbiological damage. We think of sour oil or sour gas as an economic problem, a facilities problem, a handling problem. But down in the reservoir, something's happening to generate that sour oil and sour gas. And that's typically bacteria who could be making cell mass, biomass, biopolymer, which is filling up pores potentially. That's a formation damage mechanism. So again, something that affects the reservoir through what we've done to it. That could be through giving the right food source for the bacteria, changing the near-wellbore conditions, introducing contaminants to the reservoir. So these are all typical examples of damaging mechanisms that we see. Again, there's a lot of them. It's a whole separate webinar, is formation damage mechanisms. But I mean, let's look at it at a reservoir level to try and stop talking about it in words and talk about it in pictures. What's the prize? If we think about our aim being to improve hydrocarbon recovery, what we're looking at here on the left, these are a type of electron microscope called cryogenic scanning electron microscope. And what we have here is a high rate gas reservoir. In the left-hand image, we can see that we've got grains. You can see the scale here. This is about 60 microns across this bar. So we've got grains that are couple of 100 microns across. We're right inside the pore network of the reservoir. And here, this black area is a pore. It's quite small. And here, this is a pore that's completely blocked. And what's blocking is this smooth gray stuff that's sitting all over the grains, which is actually completion brine. So what happened here was completion brine was introduced to the formation so that we could examine the compatibility. Then we produced gas, remeasured permeability. It was more than 90% reduced in permeability. And when we went and looked inside the core sample, we could see what had happened was the saturation had actually increased. So the saturation to native brine was lower than the saturation to the introduced potassium chloride, I think it was in this case, completion brine. So this was a fluid filtrate retention, saturation change issue. And as soon as you see that, you can start to understand, okay, there's a big problem here because the fluid is trapped. But because now we know it's an aqueous fluid issue, we can start to look at solutions. So you can start to say, can we look at a surfactant or a treatment fluid to remove this break the surface tension and remove this fluid? Or can we change to a different chemistry that this won't happen with? And what they did here was they repeated the study. They included a treatment fluid, which was, I think, a solvent or surfactant that broke the surface tension. And when production happened, the retained fluid all flowed away. And you can see in the right-hand image here, same rock, huge open pores. We can see the clays, we can see the grains. There's our prize. Can we predict or discover that there's damage? If there is, can we determine exactly what type it is? And then if we can remove it, we're going from a 90-odd% drop in permeability here to something like a few percent drop in permeability here. That's our prize. There's a lot of things we can do. Can we identify them and can we remove them? And what sort of new technologies can help us do that even better? So these are the things we should be thinking about in the world of drilling and completion, and then when we are coming on to production of the reservoirs, of what we should be trying to achieve with these kind of studies. So talking about formation damage, we should be trying to remove damage in the first place. If we can identify it in a well before we drill a well, we can minimize any damage, which kind of leads on into reducing the need for treating wells, recompleting wells, drilling additional wells. If we can avoid damage in the first place, then we don't have to worry about it further down the line. Of course, there's production damage, there's injection damage, there's scaling, but we're talking about drilling completion damage here. So if we can remove it or minimize it in the first place, then we don't have to worry about it later down the line. And that the effect of damage from drilling completion is loss of production. You know, earlier production is more efficient, so we don't want to be taking a long time to clean up. Shell and BP have both been quoted in years gone by that they're losing $1 billion a year of production from lost production due to formation damage. And we start to multiply that up around the world for different operators, different fields, and it's huge numbers here. So small changes, small improvements in damage can have huge impacts financially. So, you know, the guys at the top of the company love thinking about it in money terms. So for every percentage of damage we can remove, we're just getting more and more money back, more and more production back. And then deferred production, you know, if we say, okay, it doesn't matter if we lose 20% of production because it will get there eventually, but deferred production is higher risk. You know, I bet you most people would prefer to have been producing last year than this year, the current oil price. So minimizing damage and improving hydrocarbon recovery, these are kind of like the financial impacts of formation damage. That's the background of formation damage. So I don't really want to talk too much more on background. As I said, it's a whole different presentation. But you know, just what do we see in the reservoir drilling and completion damage looking like? And these are the kind of visualizations we see. So this is typical drilling damage related to either drilling mud invasion or cleanup. What we have here is a thin section. So this is the wellbore or the inlet face of the core. We have the whiter grains, the bluer pores, and we can see we've got nice blue pores here, only a few hundred micron. This is the grains, again, 200 or 300 micron size grains. So less than a millimeter from the wellbore, we've got blue pores that are open, but we've got this layer here, this gray brown layer sitting on top. That's a drilling mud cake. What's happened here? Mud cake is built up on the reservoir, and during production, it hasn't cleaned up properly, so it's blocking pores at the wellbore. In the right-hand image here, this is the same sample. Imagine we're now sitting in the well, looking back towards the formation. What you can see here is you can see this is an electron microscope image, individual grains here, and the black areas are the pore space. But what we've got, these scattered areas of these small crystal grains, looks like sugar on a donut. These are actually drilling mud constituents, of solids and polymer from the drilling mud, bridging particles, weighting particles, and some polymer there that are sitting on the wellbore of the reservoir. Some of the pores have opened up during production, but then there's huge areas where the pores are blocked or become micropores. So this is drilling damage that hasn't cleaned up during production. And you can start to see, you know, when I'll talk shortly in the kind of studies that you do to look at formation damage. This is the whole reason you do it, is to look at what the impact of various candidate fluids would be. This one is recent data, which is a really nice visual observation on the difference between the performance of drilling mud in different scenarios. So we have drilling mud water, which is an oil-based mud, and we have drilling mud 2, which is a water-based mud. You can see this is gas like the first two, and oil like the right-hand one. I'm not going to talk about the right-hand one, but if we just want to look at the difference in performance, so in this real study, this left-hand image, the oil-based mud performed better than the water-based mud, which is on the right-hand here. And it's quite clear why, because we can see that after the mud built up and we started to produce, then lots of channels, wormholes opened up in the oil-based mud cake. So basically, essentially wasn't having an impact on permeability at the end of the production. Whereas with the water-based mud, just a few of these channels, much bigger drop in permeability because the cleanup was poor. So this was the nature of the drilling fluid that was selected, comparing 1 versus 2, permeability impact, looking at the visual observations. I'll talk a bit more about that in the next slide or two as well. Right, next slide. Completion damage. So that's typical drilling ones, and it tends to relate to drilling fluid, depth of invasion, particles, solid fluids, and whether they clean up later on and whether there's retention of fluids. Typical completion damaging mechanisms here. I showed you this one before. So inside the reservoir, fluids, completion, drilling, any fluids within the operational sequence getting into the formation and then not getting back out because there's a chemical reason, a physical reason, or a combination of the both. This is I talked about emulsions or sludges. This is a oil reservoir. So I've got a grain here, I've got another grain here, and I've got a grain just sticking in here, and here's a pore. And in the pore, we've got the dark black area is oil, and we've got these spheres or dots in here. This is a submicron emulsion. So the completion fluid that was used during the well operations went into the near wellbore, formed a very stable emulsion, and it wasn't broken or flowed back during production. And then more significantly, this area here, which looks stripy, and there's another one here. These are two individual droplets of the completion fluid that are trapped in a pore throat. So there's a pore throat down here somewhere. And what we've caught in this image is phase entrapment, water block, whatever you want to call it. What's happened is the fluid has gone in this direction during fluid loss, during well operations, and then production has been from the top right to the bottom left. And these droplets have got jammed in a pore throat, and they've restricted that pore. This pore is blocked off because the filtrate or the retained fluid is blocking it off. So again, seeing what has caused that allows us to think about how we can fix it. And then there's completion hardware as well. So in a well with screens and gravel packs, we have a weave screen here and a wire wrap screen here, looking at how the sand or the drilling mud constituents block the screen. Tells us something about whether the screen is doing its job properly, where the drilling fluids are doing their job properly. Lastly, we have this one, which I like, because this one shows one of the reasons why lab simulations are useful, because in this reservoir, it was an open hole gravel pack, and we had a drilling mud that when tested alone performed really well. And the screen, when tested with the sand, performed really well. But what happened was when we added the gravel and the mud together they weren't a good combination, because we're in the wellbore here, looking back towards the formation, and we've removed the screen and we've removed the gravel, but are leaving the reservoir and the remnant mud cake. So you can see where my pointer is now. This is the open pore network below, and there's grains below. And then we've got this, let's say 50 to 100 micron thick layer of amorphous material, which is the operational fluid cake. And you can see we've got these kind of circular fossils of where the gravel has been. So what happened was the interface between the wellbore, the mud cake or operational fluid cake, and the gravel has formed a very low permeability interface, hasn't cleaned up during production because the gravel sizing was a little bit conservative. And that led to a high level of damage from fluids that were selected individually to perform well. That's a theme I'm going to come on to shortly, on what's the best practice or how can we ensure we get good data. So that's typical drilling and completion damaging mechanisms. As I said, there's a lot more. I've not talked about perforation here. I'm just showing some nice visual ones with drilling and completion. We've got perforation damage, all sorts of other damaging mechanisms during drilling and completion. So those are the types of mechanisms we typically see. And I said that the whole point of this event tonight is to talk about, how can we use advanced laboratory evaluation and visualization to identify those mechanisms. So this is a typical piece of high-tech reservoir kit. What the general philosophy behind formation damage testing, lab simulations, whatever you want to call this, is take a real piece of reservoir rock if it's available, or if not, take an analog piece of, or representative piece of material, put it to the correct near wellbore temperature, pressure conditions inside. So we have, this is a test rig, oven, whatever your air bath, whatever you want to call it, inside here. We have a core sample in a core holder. Typically these samples are 1 inch, 1.5 inch diameter, up to 2 inches, 5 centimeters in length, at reservoir temperature, near wellbore pressure, inside here. So this is keeping it all at reservoir conditions, and then simulate the well operations that we want to simulate. So sometimes we want to do something quite simple, like look at clay fines migration. What happens with the reservoir clays when we flow at representative production rates? In the drilling and completion world, it tends to be answering questions like, which drilling mud should I use, or which variation on my drilling mud should I use? Should I use water-based mud? Should I use mud? Do my completion fluid and drilling mud have any issue with each other in the reservoir? So what happens we would simulate the reservoir operational sequence in this rig. You can see this side is what we call the reservoir side. So we've got pistons where we can have oil inside inside the rig or outside the rig for oil, depending on whether it's crude oil or refined oil. Humidifiers for gas wells. Typically, nitrogen is used for safety reasons. And on this side, we call it the wellbore side, where this allows the delivery, buildup of mud cakes, injection, bullheading, squeezing of fluids. And what the philosophy in all formation damage laboratories and approaches is to try and be as close as possible, simulate these operations, then produce or inject, get to an end point so that we can compare to the reservoir and use that data to help us make decisions. And that's the kind of traditional approach, which I'm going to talk a little bit more about before talking about how can we take a better approach, more high-tech approach. So that's the typical wellbore condition simulator. You'll see lots of different types of this. This is our particular one. And the kind of typical data sets you see coming out of these simulations are these. And I think it's important to show you that there's good and bad sides to these, because it leads on to my argument I'm going to make that there's a better way we could do it as well. Because this traditionally within industry, you'll get a table with results, typically these kind of 4 main data points in a report. And they tell us a story, but they don't tell us the whole story, because you can see, for example, permeability measurements. When everyone thinks about, have we done a formation damage test? Have we tied our mud? Well, typically the first thing people look at is a graph or the table that has the initial permeability and the permeability after, and they want to see how much of a drop it is. And that's why I've got the major benefit of permeability is benchmarking and comparing. We can compare between wells we've done. We can compare in the same well between multiple different vendors or fluid options or bridging options or mud types. So it's fantastic for that. But we have to take it with a pinch of salt and be very careful with how far we take the interpretation of permeability. One of the compromises that is related to the core that we retrieve from the reservoir is that we tend to only have short core samples available for these kind of simulations. So as I said, up to a few centimeters long. So there's a high potential that we can have, for example, let's say drilling mud invasion of solids goes all the way through the length of the sample, and that reduces the permeability significantly. And at the same time, during production, we remove clay fines or we have some sanding, and that improves the permeability by a roughly equal amount. Overall, we might see a few percent either side of zero change and think we've got a great result, because that's a short core sample. It's relatively easy to remove clay, for example. Or when we scale that up to the reservoir, we might have a concentration accumulation over hundreds or thousands of meters where you don't have a chance for the clay to escape 5 centimeters of core sample. So permeability can be potentially misleading in short core samples. So just using permeability can potentially be a little bit dangerous. So we've got a question here from Elewa Ahmed, which is, when we talk about core length, what is the optimum core length for formation damage simulation according to our experience? That's a good question. So ideally you have a nice long core sample, so as long as you can fit in your core holder, or let's say where we can get deeper than the depth of invasion of solids and fluid, but that's going to be multiple feet, which we have to be realistic about isn't possible. We have to take these compromises. And so because our primary aim is to use real reservoir core, and the typical samples will be horizontal core samples, so that means you want to take a sample along the bedding plane. And in a typical core, let's say a 4 or 5 inch diameter core, because the core is cut perpendicular to the bedding, that means it's going to be the 4 or 5 inch diameter is going to be the longest possible core you can get, which is along a horizontal bedding plane. So forget about our ambition to have 10-foot long samples. It's not realistic. It's not possible. We're limited by the core. We have to take samples to remove any invaded zones from the core. So realistically, two inches or so is the longest that anyone will use for core flooding like this, because it's the longest we can get that guarantees a core that's not been invaded, is horizontal along a bedding plane, and is going to be representative of the reservoir. Sure, if you have outcrop core, you can start to do longer samples, but we're trying to be representative of the reservoir. Another couple of bits of data. I won't talk about these in as much detail, because perm is the one that everyone thinks about. Filtrate loss volume. So thinking about mud, completion fluid that goes into the reservoir, how much, how fast, and if we're using a treatment fluid, how long does it take to break through? This is fantastic comparative data. But then again, it doesn't tell us how deep the invasion is. You know, if I take a core sample and I say I've lost 1 pore volume of fluid, so this the equivalent of 1 volume of the porosity of the core has gone into the reservoir. Does that mean that it's gone exactly the length of a core sample because it's one pore volume? Yes, if there's piston-like displacement, but we all know that's not what happens in real life. In real life, it's going to channel and wormhole and go, it's going to shoot along some high perm streaks. So in reality, when we see one pore volume losses, that's the bare minimum. That's the minimum level of invasion there's going to be in. It's a guess. You can't really, you can say it's high loss, low loss, looks good, looks bad, but we can't say the depth of invasion. So we'll keep that in our mind for later on as well. But how do we spot that? Production injection rates, like clean up, we can look at production rate versus time, and we can compare samples looking clean up. But it can be quite confusing because if we're at the same time as cleanup happening of the mud cake, we have clay fines moving or sanding or precipitation happening, we could see no change in the rate, or we could see a dropping rate when we're actually cleaning up a mud cake. So again, good broad indications from that data. And then last up, visual observations. I showed you the pictures of the drilling mud. It's a good first look at cleanup, but not necessarily comparing samples. It doesn't show us inside the samples. It shows us what's happening on a large level. Mohammed has asked, how about NMR and sonic permeability, since core samples are expensive? Yeah, core samples are expensive, but I mean, again, it's a subject for a different one of tonight, is, in terms of value for money. I think that many, if not most operators, will do this kind of core flood testing because they find that it pays off multiples of what they spend on it in giving them usable data. Same with the core analysis. So yes, there's a certain amount of prediction of damage you can do from all sorts of well data, but nothing's going to tell you what really happens with your reservoir, with your fluid, with your conditions, other than taking your core, your fluid, your potential drilling completion fluids, and putting them together and seeing what happens. There's no such thing as a reservoir formation damage simulator because there's way too many variables that can be on a bed-to-bed basis. So now on to just a couple of slides on some of the ways that, how can we move from these traditional metrics and data that I talked about here to giving better data. Now, one of the things that's typically done in the formation damage world within vendors, within operators, within labs is we're drilling a well, let's just look at the drilling fluid alone and use that as a metric. So this is real data here. And this is an open hole standalone screen reservoir where, sorry, one sec. This is an open hole standalone screen reservoir where we have the well was drilled. It was followed by screen running fluid, and then there was a standalone screen at an offset from the reservoir. And there's two ways you could look at that. The one option is to say, well, the screen, we're just going to test that with the mud. That shouldn't be an issue. So we can ignore the screen. Let's just look at the mud. That's the important thing for us to get right. And true, that is the important thing to get right. So we did one set of tests. So it's 3 muds, formulation A, B, and C, with 3 rock types here. And we have different muds here. And then on the right hand here, we have the second set of data where we included the screen running fluid to displace the drilling mud, and we included the screen. And on the face of it, the results, just eyeballing them, look similar-ish. Then start to compare some of them, and I've highlighted these ones here. So this is the same drilling mud, same formation. So we've got lithology 2, which is rock type 2, and we've got formulation A and C. So we've got 2 drilling muds, same rock type. And you can see here, I've circled this area, and you can see. So just to explain what I'm showing here is the data we have here is we've taken the initial permeability measurement on the core sample, built up a mud cake against it, produced, then remeasured permeability. And that's what this red block is here. So if it was 100, it would be the initial permeability. Here it's about 75%. So we've lost about 25% of the permeability after flowing the mud. And then we have removed the external mud cake and remeasured the permeability. That's what this blue block is. So in this case, it's gone up slightly after we removed the mud cake. And then finally, we've done what we call spin down. It's centrifuging. Basically, again, won't talk about that in detail, but we're looking at what mobile fluid there is that could potentially be removed from the reservoir. So again, looking at fluid trapped within the reservoir that could be removed and remeasuring power. And that's what the 3 data points are. So looking at this particular sample, number 5 here, 75% after mud application and production. Then the same test, the only difference being that we displaced the drilling mud with a screen running fluid and remeasured and included a screen. We've gone from 75% down to 60%. So we've lost 15% of the permeability from just from adding in the screen running fluid in the screen. So then the way that the mud cake behaves is different. Having the screen there is different. So the traditional test, which is just look at the drilling mud separately from the mud, has given us different data sets. You can see it here. This is one that shows us, and I like this bit of data here because this shows us here. So with this mud, we were at 60, let's say 65% with this relatively small blue block when we removed the mud cake. So the mud cake wasn't really having an impact on permeability. As soon as we added the screen running fluid in, it changed the nature of the mud cake, by displacement, maybe interacting with the mud. And we've gone from a small blue block to a really big blue block. So just having the screen running fluid changed the mud cake when we displaced it through. Wasn't even high losses. So the first thing I'd like to say about making sure we get better test data is make sure we're testing full operational sequences. It's more difficult. It's relatively easy to say, I've got this bit of kit, I'm just going to throw some mud against a sample, produce oil or gas through it and measure permeability. But then making sure we're doing something meaningful. If we took the left-hand one here, we gave a different picture from the right-hand one here. So in terms of what is an advanced laboratory simulation, the first thing is to make sure it's done at reservoir conditions and to make sure we're simulating maybe individual fluids separately as well, because we want to know how the mud behaves. We want to know how the completion fluid behaves. But it's extremely important to consider the full operational sequence of what impact that has on the reservoir. I'm just looking at a couple of questions here. During completion and displacing hole to brine, we have losses and the brine going to the formation. How can we mitigate this risk? That's a really good question. So, high losses, there's two ways of mitigating the risk. First thing is to find out, is high losses actually hurting your reservoir? It may not be. In many reservoirs it will be, but in your one it might not be. So first question is, does that hurt my reservoir? Simulate that, see if that happens. If it does hurt the reservoir, then we've got two options. Can we stop the losses by looking at well operational fluids, like resizing the drilling fluid, for example, or looking at LCM or healer pills? So looking at stopping the losses is one option. And then if that's not an option, can we look at treating that damage once the fluid's gone in? If it doesn't come and it's, can we, firstly, are they a problem? And secondly, if they are, do we avoid them or remove them? And then what have we got here? Can we apply these? So Hastin is asking, can we apply these measurements to the shell reservoir? Absolutely. So I'm showing lots of clastic pictures tonight, and they can be applied absolutely to matrix in carbonate reservoirs. When we're talking about fractured carbonate reservoirs, it's a slightly different subject, but absolutely formation damage studies are done, mainly concentrating on fracture losses and fracture cleanup. But we're absolutely talking about some of the same things as we are here. So absolutely with carbonates. And just the last little section before I go on to visualization for the last little 10-minute section of the presentation. So when I'm talking about advances and advanced laboratory evaluations, here's some of the things we need to think of. So I've covered what information are we trying to gather. Making sure that we get, as technology increases, we can get closer and closer to being exactly the same as the reservoir. This is vital to us. So, doing a test at room conditions versus reservoir conditions, using the technology available to get closer to reservoir conditions is going to give us better data, more meaningful data to make better drilling decisions. Because, fluid behavior will change, viscosity will change, near-wellbore temperatures and pressures, very important. Capturing everything as close as possible. If we're looking at an acid, for example, typical acids could, every 10 degrees centigrade increase in temperature could double in the effect that they have on the reservoir, double in the strength of the acid, essentially. So making sure we're as close as possible to reservoir conditions is, and using the technology. So I'm showing you some pictures of, I showed you a typical test rig there. This is a kind of high-tech one here, where you can see that's the same type of piece of equipment here. But then thinking about things like production, it's very easy to say, we'll just flow oil through a core sample. But in high permeability reservoirs, flowing oil at a high rate through it might actually end up, you're not able to heat it up properly. So you might hit cold oil in the sample, which creates an artifact. So I'm showing you a bit of equipment here that allows proper heating of oil before it hits a high rate or a high permeability sample. It's something that the industry hasn't really talked about, is, what happens when I'm producing at a high rate. But we know from the research we've done that can have an impact on studies. So making sure you're getting as close to the reservoir conditions as possible, using the right fluids in the sequence, and not having artifacts caused by the equipment. And that can mean doubling the size of them, investing huge amounts of money. Unfortunate thing for someone who wants to start a formation damage lab is it's expensive hobby to have, is to buy the kind of pumps you use for this test. This is for injection. I'm not going to talk about injection just now, but when we come down to it, a well-designed and well-executed study under representative conditions will provide useful data. So the people on this call, drilling completion guys, can say, I'm happy you've done a good study for me. You've done it high tech. You've given me some good data sets. Now I can start to use that to make good decisions. I've spent a bit of money to say, I'm considering these drilling fluid options, these completion fluid options, rather than going in blind to my reservoir. I've got some data. So that's formation damage laboratory simulations in a nutshell. But then I've introduced throughout this presentation some kind of caveats about there's things we're missing, and that's where the visualization aspect comes into it. I'd just like to talk about at the end. So I think we've got to really answer 3 questions if we want to really give you a good picture of what's happening in your reservoir, might happen in your reservoir. And I think we've got to answer the questions: what has happened or what might happen, where will it happen, and why has it happened? And I've talked a lot about what already. So what happens is through the simulations, through measuring permeability, fluid losses, measuring the production rate and production pressures, looking at the sample. So I'm not going to go back onto that. I'm just going to talk for the last few slides about where and why, which is visualization. So where is a technique called 3D alteration modeling that we've developed, and we've written a couple of SPE papers on this. I'll show you a little bit of data from it. If you're interested, you can search for Corex or my name or Ian Patey's name on SPE, and you'll see lots of examples of this. And then why is zooming in on the pore network. So the where question is an interesting one. Is, we can't smash core samples open and look at them, the whole sample with an electron microscope or a thin section at good resolution, because you just can't capture the entire sample. This technique is called 3D alteration modeling that we've developed, and it's a visualization technique using micro or nano CT scanners, where we take a scan of the core sample at reservoir, saturation reservoir, initial conditions at the start of the test. And this is typically 1,000 scans each in the X, Y, and Z direction. And that gives you sub 10 micron resolution, a data set of 15 gigabytes in this image here, might be 15 gigabytes worth of data. And then we do the test or the simulation on the sample, rescan the sample at the end point, which is the after here. We can see there's something on the outside that wasn't there before. But what we can't see is what's happening inside the sample, which is it deep damage? Is it shallow damage? Really important question for drilling and completion damage. So what the process we developed is to take these 2 data sets, load them into a computer simulator, real data sets captured from the sample, 15 gigabytes a piece, overlay them on top of each other, line them up perfectly grain to grain using the computer, and then use an algorithm to compare every single point where the data sets intersect, which is like 300 million points, and say, are you the same or are you different? If you're the same, go invisible. So in this sample here, we can see most of it's gone white and invisible because most of it's not changed. But if you are different, give me intensity of change based upon the density you see in a CT scan. So here we can visualize the depth of invasion of this drilling fluid. So we can see the external mud cake hasn't cleaned up properly. And then we have a few millimeters into the core sample. We have significant operational fluid constituents. You can call it an internal filter cake if you want, in the first few millimeters. And then deeper into the sample, we've got lots of scattered pores where there's change. But the most important zone in this particular study is in the near-wellbore. So now we can answer the question. I saw a 50% reduction in permeability, and virtually all of that was in the very near-wellbore. That's a good answer for a cased and perforated well, because that'll be bypassed. If this is an open well, and this is a calcium carbonate drilling mud, it's a great candidate for acidizing to remove or breaker to remove that damage. So understanding where it is really important. It allows you to compare differences between fluids. This is the same rock type with 2 different drilling muds, and this one on the right was a worse result than the one on the left, and we can see why. Here's the interface, the inlet, the wellbore of the core. There's a mud cake, remnant mud cake at the end of the test, invasion in a few pores, which a mud should be doing, and then deeper into the sample, it's black. There's no damage. Good result. On the right-hand image, we had a bad result because we could see there was change going right to the bottom of the sample. This is an example of the question of how deep is the invasion. Here we can answer. There's invasion along the whole length of the core sample here, and it's actually pooling in the back end of the sample because filtrate is getting trapped and it's not flowing away. Filtrate's been removed from the near wellbore during production, but not from deeper into it. So here we can identify deeper damaging in the reservoir, so comparing fluids. There's a question on fines migration. We'll leave that open and I'll mention it at the end of it. So at the end of it. We can also see unexpected behavior with this technique. So this is a Middle East reservoir. And what we can see is this is a drilling mud filtrate loss graph. And this is fairly normal shape for water-based mud. But what we actually had was an unexpectedly steep start to the curve. In other words, the spurt losses were high. So traditional data sets would say the filtrate loss was high, the permeability result was bad, there was something wrong with the drilling mud, but you might not know precisely what that was. When we loaded it into the CT scan and did our 3D alteration model, what we actually saw was there was some remnant mud cake here at the face of it. And then we saw these streaks here where there was lots of change in the core sample. What they did was they lined up perfectly with, you can see these red zones here where the larger black spots are. These are bigger pores. So what happened was the drilling mud was optimized for the average pore throat size, not the maximum pore throat size. And during drilling, the drilling mud filtrate shot down along these high frosty streaks in the reservoir, and then during production they were completely bypassed. So this mud was optimized for the middle pore throat, and in the maximum pore throats it went down there, and essentially this drilling mud damaged the best permeability zones. So if they wanted to optimize it, they would have to look at bridging it properly for the larger pore throats, and that was a conclusion that we could only get from this visualization technique saying where it went. And I'm just going to show you a couple more examples before we stop. Is mudcake, question here from Usama, is mudcake recommended against permeable formation to avoid formation damage due to drilling mud? That's the key of why we do these kind of studies, because the drilling mud has got to stop losses into the formation. It's got to take cuttings away, it's got to lubricate the drill bit, but then the flip side of that is it's got to limit the damage from losses, but then it has to clean up during production, or if we're perforating, we have to get past the damage. So that's one of the main reasons we do these studies, is to say, does it do its job of limiting losses and limiting damage during the drilling phase? But then drilling doesn't exist on its own. We have to complete and produce as well. So then we have to think about what's the production properties of a mudcake as well. But absolutely, we always need a drilling mudcake there if possible, unless the formation can take high losses. Just going to show you one more example. And again, if you're interested, look at our SPE paper on this one. So this is just to show you the kind of interpreting results which are difficult to interpret. What we've done is scanned before and at the start point, and then rescanned it at sample point 1, which is what these orange images are here. And then we've looked at point 2, the difference between 1 and 2 is what these green images are. So if all the damage here disappears here, it'll be a mirror image, which is actually what's happened here in sample 6. It's basically a mirror image. And in sample 5, it's not. So what's this data showing us? We've got sample 5 and sample 6. We've got the same mud formulation, but 2 different formations, and they perform differently. And why was that? And what we can see here is, you can see in sample 5, there's damage, and you can see it's gone about 1 centimeter into the core. There's mud cake sitting outside it. And then when we've gone to this end point here, remove the external mud cake, remove the fluid. The green is the kind of where the damage has been removed. But this whole area here hasn't been removed. So there's damage still deep inside the near-wellbore here. It's 5. So with rock type 2, the damage went into the reservoir, and only the very near-wellbore damage was removed at the end point. Whereas in this sample here, which is lithology 1, sample 6, it went a bit deeper in than you can see here, but then it all disappeared. The green mirror image of this shows it all disappeared. So it cleaned up much more readily. So essentially the question there about drilling mud filtrate, it wasn't damaging in this zone, but it was damaging in the other zone. So this is the kind of interpretation we can get. Ibrahim Ahmed has just asked, can the mud filtrate simulation estimate the skin factor? Skin is very difficult because we're looking at a certain number of variables in lab testing, but what you can certainly get from these kind of studies is inputs to trying to scale up skin factor. We'll measure things like permeability rate. We know that. So it can be used in, if you want to try and take that data and extrapolate it to skin. We don't necessarily do it, but it's not out of the question. And then the last thing I want to very quickly talk about is, I want to leave a few minutes for questions at the end, is the why, which is geological techniques. So we've got the where, which is where in the near-wellbore do we see the damage? That's with the CT scanning, the 3D alteration modeling. And then what we do is we zoom right into the pore network and use things like thin sections to look at the distribution of minerals. scanning electron microscope. We call it dry SEM, where we look at without fluids, and you can look at drilling mud, solids invasion, clay fines migration. And then we've got that technique I mentioned called cryogenic SEM, where you can see fluid distribution. And when you start to try in these traditional techniques with the innovative techniques like visualization I showed you there, you can start to build up an overall picture of what's happening. You can start to relate it back to the permeability. You can start to say, look, we saw this zone here of intense change. We've zoomed into that using the electron microscope, and we can see that this zone here is from drilling mud solids blocking all the pores. We use the EDS, which is energy dispersive spectroscopy, a scanning probe, to show us that we actually saw fluid. These dots in the near-wellbore are fluid, the reservoir fluid being retained. And then deeper into the reservoir, we use the electron microscope to see that there's clay fines migration and accumulation in the reservoir. So I think this demonstrates the kind of what I said. You want better data. You want meaningful data. You want meaningful interpretation. I propose that we should always be asking what has happened or what may happen in the reservoir by simulation as close as possible, using reservoir conditions, where it has happened by this 3D alteration modeling, and then why it has happened using traditional geological techniques. And it's only by combining all of this together do we get the real sort of criteria and metrics to allow us to make better decisions or good decisions. We can say, look, here's the evidence for why we've chosen this drilling fluid, or we've had a problem with a well. We've replicated it in the laboratory, we've simulated it, we've found out exactly what happened, and this is why we've chosen this way of remediating it. This is why we've chosen acid versus solvent, for example. So that's the kind of guts of what I want to talk about. I just want to show you a Middle East case study to show you the kind of value you can get when you see unexpected things. Because again, lots of formation damage tests show you what you expect. This was one where we have a sandstone. It was a operational sequence which included drilling mud, a solids-free displacement, drilling mud displacement. It was a screen running fluid. There was a screen in the reservoir, and they saw damage from the drilling and completion. So they wanted to include a treatment fluid within the wellbore sequence. So they included an acid in there. The acid was lost into the formation very rapidly. When we remeasured the permeability, it was a pretty good permeability result. But then we went and looked at the scan, and you can see this is the sample after, and all these orange areas are the retained or the uncleaned up drilling mud cake. So what we actually had there was mud left on the outside. So the question straight away was, how come we saw a good permeability result? Did the acid not work properly? And that's when we use this technique. And I told you we can sort of model and see where the changes are in the core samples. So what you can also do, a part of that, is you can actually look at the framework grains, and you can look at the change in the volume of them, and you can look at the pore volume change. So you can actually see specifically where the change is. So that's what we did here, was we went inside the sample, and you can see the orange here where we had drilling mud that wasn't there before. But then we used this pore volume change and the framework grain volume change to show us what had happened. What we're actually seeing is these blue areas at the wellbore here where some sanding has happened and some clay quartz has been removed. But this is what caused the change in permeability to be positive. It was the near wellbore, or in the wellbore, cement. There was a calcium carbonate cement in the reservoir, and it was dissolved by the acid treatment. So what we have here is an example of where a treatment fluid was designed to treat drilling mud. It didn't do its job. It didn't remove the drilling mud. What it did instead was do a near wellbore acid stimulation. So the question is here, were they happy with that? Because there could be wellbore integrity issues with the acid. They might want to remove the drilling mud, so they might need to look at an acid that's less rapidly reacting, that eats away the mud cake more slowly and isn't lost into the formation before it does its good job. So that's the kind of conclusions that we got from the 3D alteration modeling. And as I said, this is a Middle East clastic reservoir. Again, this can apply really equally to carbonates, low perm carbonates, chalks, matrix carbonate reservoirs. Looking at fractured carbonate reservoirs is slightly different, but this is nice visual stuff to show you here. The last slide I'm going to show you before we stop for questions is just to show you where this is going. So I showed you these kind of qualitative techniques, and I said I was going to show you where the state of the art is in the industry. This is something that we've received a patent for recently, which is looking at combining multiple scales of resolution of analysis using micro CT and nano CT and electron microscopy and specialist electron microscopes called focused ion beam, and combining all that in a simulation and using algorithms to basically individually segregate damaging mechanisms. This is where we're going to be going in the industry in future, which is to be able to take a piece of rock non-destructively before and after and say, in this reservoir, when we did our simulation, we saw that there was 31% change in permeability. The vast majority of that, 25% of that, was from the drilling filtrate retention in the pore net, where you can see this green change here, with a small amount of clay fines migration and a small amount of drilling solids. So that's just the last slide to show you where the industry is going to be going. Watch this space. This is going to be used for adding extra value to core flood testing. You're going to see this, I'm sure, being adopted by industry. And then you can see this is in the kind of format that can be outputted into inflow models and computational fluid dynamics to give better upscaling of results, because understanding what core flood test data means on a reservoir scale is a whole different webinar as well. So that was the last slide. So again, this is a huge subject, so I just wanted to touch on a few things tonight and show you some of the technologies that allow us to determine damaging mechanisms, some of the conclusions that can be made, and maybe just get the point home that, you know, it's a difficult job drilling wells, completing wells. There's a lot of pressure at the moment, so doing our job right with getting as much data as possible, from my viewpoint as a lab guy, is vital to making sure everyone can do a good job. So hopefully everyone saw something interesting. I see there's a couple of questions. And I think Nasir said if we have time, we might have some more questions.
We could definitely take these two questions. First of all, thank you, Justin. Excellent presentation. I'll enable an option for those who want to ask a question, not by typing because they have a long question or a comment. So you would see a raise hand button at the bottom of your screen. Click on it, and we'll try to allow some of you to kind of speak and ask questions. I'll let you, Justin, answer some of the questions that you see on the screen.
Sure, I see 3 questions there. So I'll just answer them in the order that they have them. So first up, we have Marcelo's question, which is, do you think the industry has to move forward to find a better way to test the compatibility of the drilling mud with the reservoir? 100%. Obviously, what we have to be striving to do is to be constantly finding a better way to test the compatibility. As I said, we've got, you know, you can start off extremely basic, take a bit of ceramic disc, try a leak off test against that and see if the mud is good. And then you start building into that what I've been talking about, which I think is way better than we've been doing in previous years, which is to get closer and closer to reservoir conditions. But then you could argue you want to look at larger scale, you want to look at radial flow, whatever. Yes, we should always be striving to be more representative. As I gave an example, looking at high rate samples and whether drawdown in the lab can have an effect on that. Everyone should try to be innovating all the time to get better results, better data for you. Abdulaziz asks, during the drilling process, filtrate measured in the lab using static fluid loss cells to simulate volumes of filtrate invaded. But do you think this Eval test, considering the reality, dynamic fluid loss test can be simulated to reflect actual process to measure fluid loss, which will show higher magnitude? Excellent question, Abdulaziz, and I 100% agree with you on that as well. I didn't dive deep into, again, it's a separate webinar, is how do you do these kind of studies? And yes, in certain situations, laboratories will just do a static fluid loss cell. I should have said the kind of core holder and test rig that's used in high-tech lab testing is fully dynamic. So if you see a bit of the lab data I showed you here with the filtrate loss, that was fully dynamic filtrate loss. So you absolutely have to capture that to get meaningful data, Abdulaziz. An anonymous attendee has asked, is there any plan for automation and real-time application? 100%. So, you know, there's some degree of automation existing in all equipment. There are some fully automated systems. There are some systems that are not fully automated. There's actually a benefit to having people involved in the process because they know what they're doing a lot of the time. And real-time application, real-time data from core flooding, and also from things like sand control testing with real-time scanning and real-time scanning of these 3D alteration models are something that I'm sure we're going to be looking at over the years as well. So real time is going to be important as well. Hassan asked, what is the difference of formation damage effects on carbonates and sandstone formations? So I suppose, I guess I've hinted at it a little bit. It depends on whether we're talking about, matrix or fracture in the carbonate world. In the sandstone clastic world, we're thinking about pore networks, what's in the pores, the minerals in the pores, do they clean up? The fluid in the rocks, does it interact with them? So we're looking at native minerals, clean up of the pores, clean up the drilling fluids. And that's exactly the same in matrix carbonate production or injection, because again, we still have minerals there that we have to have compatibility issues with. We might not have clay or as much clay, but we still have native minerals. We still have fluid loss to consider and where that cleans up from the pore network, especially with low perm carbonates. You know, the lower perm the sample, the more pronounced the effect of losses of solids and fluid could be on the reservoir. With fractured carbonates, it's more of an issue of we need to think about what are the losses into fractures, does that clean up? Do they block off, do they not block off? So it's a slightly different area. With shale, coal, then we're thinking of other things as well. So we're thinking about things like proppant and bedment and gelling and all that stuff. So there's a range of different things. So yes, formation damage is extremely relevant, but you know, the point I made in the midpoint was you want to make sure your scope is reflecting your reservoir. So the way you design the test should really reflect on the reservoir type, and you might do a slightly different test for fractured chalk versus a matrix chalk, for example. So there are things to think about. Then Hussein has asked, is the density of the mud affecting the test? 100%. So what we're trying to reflect, one should be trying to reflect in a laboratory simulation is the well simulation, the well conditions. So in the well, the higher the density of the mud, the higher the overbalance pressure will be, and the higher the potential losses or the nature of the mud cake might change. So in laboratory simulations and visualizations, we should be reflecting that. So if there's a higher density mud, we should be reflecting that overbalance pressure the same in the lab. So if there's one mud is giving us an overbalance pressure of a few hundred PSI and another one is giving 1,000 PSI, we should be looking at those and looking at those options. So the density of the mud and including that in the test design and understanding what impact that has is 100% important. And that's a typical thing that operators look at. They look at, you know, what happens, is there a difference between these two SGs or densities of mud? Is there a difference when I add this drill bit lubricant or the friction loss, friction reducers? Do these make a difference to the mud with and without them? These are really classic questions we ask in drilling. And in the field, we only find out when we drill 2 wells and see the difference. The whole beauty of having lab simulations is you can muck around in the lab. Sure, it's for a cost, but it doesn't cost for 1, 2, 3 simulations in the lab what it costs to drill a well. So density, overbalance, exposure, length of time of exposure. If a well is going to be shut in for a year, do you do a test that has a well, you know, the mud exposed for a day, or do you do a test that has exposed for weeks or months? We could see very different results. I'm giving a webinar later this week on long-term shut-in, and we've seen that you see different results. So you ask about density of the mud affecting the test. Everything affects the test. Every condition change affects the test. This is why many, if not most operators, consider this a vital building block of making good drilling and completion and production decisions, is making sure that it checks out in the lab first before it ever sees the field. Thanks, Hussein.
I can definitely attest to that, Justin. I've worked in a lab for a couple of years using ovens at 100 Celsius. That was not fun at all, and just 1 minute of opening the door and closing up kind of changes everything and all the behaviors. If we don't have any other questions, I'll be waiting for another minute or two for you, ladies and gentlemen, to think of any questions. Either raise your hand to speak up or just type it in the Q&A box. Meanwhile, I would like to remind you all of the survey that we're asking you to fill up. I have the link in the chat. If you can see it, that would help us, SPE KSA, to better cater for you or to you about topics that you would possibly like us to kind of discuss or invite people to talk about, like much we have Justin talking to us tonight.
Well, thanks for your time and attention, everyone.
All right, I guess, thank you, Justin. Really appreciate your time tonight. Also, thank you to me, Dad, for sponsoring this webinar this evening. And goes to everyone, please check our Twitter account, our LinkedIn and Instagram. They have all the announcements go out in there. So we have another webinar coming up in a couple of days. That's more on the soft skills, kind of professional development rather than technical. And we'll be having more of the technical webinars coming up very soon. Thank you, Justin. Appreciate it, and have a great evening.
You're welcome. Have a good evening, everyone.